Okay, hi everyone. My presentation is on quantum program verification and quantum horror logic. The project is not a technical proof of quantum horror logic itself, but a research landscape analysis. So I use Scopus data, bibliometric science mapping, bird topic main path analysis, critical review to understand how this field has developed and how verification sits inside the broader programming language literature. So why does this matter? So the motivation is that quantum computing is often discussed through hardware progress and algorithmic speedups, but software correctness is equally important. And quantum programs are not easy to reason about informal statements because they involve quantum state evolution, measurement, probability, and entanglement. And so quantum Hall logic is relevant because it adapts the idea of Hoare style correctness reasoning to quantum setting. And so the project asks, how has this verification research developed inside the larger quantum programming language field? And so the final aim was to analyze the research landscape of quantum programming language with a specific focus on quantum program verification and quantum Hall logic. So I used two objectives. The first one is about bibliometric structure, publication trends, contributors, and collaboration patterns. And the second objective is more thematic. It identifies the main themes and it explains how quantum Hall logic contributes to correctness, reliability, and the theory. And for data collection, I used Scopus. I tested several searches, and the first search, quantum logic or quantum algorithm, returned nearly 62,000 records and was far too broad. So I got the final query here. It was a quantum programming language, giving 2,697 records from roughly around 1967 to 2026. And this query, in my personal view, was broad enough to capture the wider programming language field, but it also introduced several noise. However, I treated that as a limitation instead of pretending that the dataset was perfectly focused. Next is the methodology. So the methodology was designed as a pipeline. So Scopus defined the corpus, VOS viewer helped produce bibliometric networks, topic identified semantic topic structures from titles, abstracts, and keywords. In main path analysis, trace citation trajectories. And finally, critical review was needed because the tools do not explain the conceptual meaning of papers by themselves. And this combination helped me avoid relying on just one method. All right. So the VOS viewer outputs the first layer of results. The co-authorship map suggests that the field is fragmented into smaller research groups rather than just one dominant collaboration network. And the keyword map confirms that the relevant concepts such as semantics, full methods, Hall logic, and programming language are present. However, it also reveals noise from neighboring areas, unrelated areas, chemistry and scientific computing. But I think nevertheless this was useful because the maps become diagnostic tools as well as result tools. So bird topic was used to identify semantic structure in the text fields. As we can see here, the elbow and silhouette plots help the cluster selection. But But I did not rely only on a single metric because my lowest K values was too coarse. So the inter-topic and document topic visualization showed the data set is semantically diverse. The key point is that verification related papers are present and they sit inside a much wider quantum computing and programming language space. So when I inspected the topics, topic number 2 was important because it captured semantics, calculus, categorical programming, and also topic 19 was the most directly relevant because its keywords included quantum programs, logic, semantics, Hoare style, correctness, and this gave me evidence that the verification theme is not just something I impose on the data. It appears as an identifiable semantic region. But at the same time, other topics showed me the noise and breadth of the data set. And the main path analysis gave me the historical layer of the project. It extracted 3 major trajectories with 68 path records and 43 unique papers. The most important interpretation is that the field does not develop one simple line. There are overlapping paths, early language design, semantic foundations, practical frameworks, explicit verification. So the paper, Dante and Panagadan's work on quantum weakest preconditions is especially important because it links semantic foundations with correctness reasoning. Now, as we can see here, the key papers show a clear transition. Early work by Bentley, Salinger, Van Tonder, and Akenkich and Gratich focused on how quantum computation could be represented in quantum programming language form. In 2006, quantum weakest preconditions made correctness reasoning much more central. And later, Q-Wire and Q-Sharp connected theory to a more practical language frameworks. Now, from 2022 and onward, papers like Twist, CoQ, QBC, and expressive assertion languages show a shift towards a more mechanized and proof-oriented verification. Now, the critical review identified 3 transitions. First is from architecture to semantics. So before verification is possible, the field needs a precise account of what quantum programs mean. And secondly is the transition from semantics to correctness. Now, the weakest preconditions and Hoare-style reasoning translate program meaning into correctness claims. And the third transition is from theory to mechanized verification. Now, recent papers try to make reasoning usable, improve assistance and software frameworks. Now, the major unresolved tension is balancing expressiveness, usability, automation, and scalability. Taking all these together, the methods show a consistent story. VUS viewer shows the field is broad and fragmented. BERT topic helps locate verification correctness theme. Main path analysis links early language design into modern verification frameworks. Critical review explains conceptual transitions. The main limitation is that the search query was too broad. And also, the citation paths depend on available metadata, and topic modeling cannot replace close reading. Now, these limitations are important because they define what the project can and cannot claim. Now, next is the social impact. Social impact is that if quantum software is used in areas like chemistry simulation, optimization, or cryptography, and incorrect programs could lead to misleading results or false confidence in quantum advantage. Formal verification reduces that risk by making correctness claims to be more precise. Now, the ethical impact is accountability. Instead of treating quantum software as a black box, verification asks researchers to state assumptions, specifications, and proof obligations clearly. Now, for future research, my project suggests moving toward a more focused data set, comparing scopus with Web of Science, for example, and reviewing works that is related to verification and correctness by construction. So the broader impact is that quantum horror logic can contribute to a culture of trustworthy and responsibly validated quantum computing. So in conclusion, the main answer is that quantum program verification is not an isolated niche. It is structurally meaningful. It is a structurally meaningful strand within quantum programming language research, and the field moves from early language design to semantic foundations, and then toward explicit correctness reasoning. Quantum weakest preconditions are a key bridge in this movement. Recent work such as CoQ, QBC, and expressive assertion languages shows that this area is becoming more mature, and future work should refine the dataset and compare multiple databases. And these are the selected references used for presentation. Thank you for listening.